Hello everyone. I have already uploaded the last topic of the section 2.4 and on Canvas. Today I'm going to start the last section of this chapter 2, 2.5, inverse functions. Our goal here is to create a function which undo what another function does. So let's take we have a function f, and if you input the value x to the f, it gives us output as y. Now we create another function called g, which does the reverse operation. So you are plugging y to g function and it gives you output as your x value. So this function is called an inverse function. So before talking about inverse functions, first we need to talk about the one-to-one functions. We say a function is one-to-one if it has no two ordered pairs with different first coordinates and the same second coordinate. Let's look at an example. Here is a function y equals x to the power 2. In this function, you can see that here we have two different inputs, negative 2 and positive 2, but with the same output 4. So that means this function is not one-to-one. So if a function is one-to-one, then every element in the domain corresponds to exactly one element in the range. But in here is totally different. It's like two different values corresponding to same exact value in the range. So that's why this function is not one-to-one. So whenever you have a graph of a function, and if you draw a horizontal line across the graph, if it crosses more than one point on the graph, so that means it's not one-to-one. Again, you can see it in here. You can consider this line as a horizontal line across the graph. It crosses two times on the graph, so that means it is not one-to-one. That's another way of identifying one-to-one, not one-to-one functions. And for each horizontal line you draw across the graph, if it doesn't cross more than one point, then it is one-to-one. So let's look at an example of a relation here. In this relation, our question is to determine whether these are one-to-one relations or one-to-one functions or not one-to-one functions. Here this relation is not one-to-one because it's if you input the value 4, you can get 16, and also if you input the value negative 4, you can get 16 again. Another problem here, for 2 you get 4 and negative 2 again you get positive 4 here. So that means this is not one-to-one. Two different inputs with a same output. That's the problem here. So this is not one-to-one. But you don't have that situation here. Each input is different and output is different here. So 1, 2, 3, 4, 5 and 3, 5, 4, 9, 0. So this is no one-to-one. So it's easy to identify whenever we have relations. But how do we identify with the given functions like this? We know that the absolute value function is not one-to-one. It's easy to see that because it's the same value it gives us, whether it is negative or positive doesn't matter, it always gives us the same value. If you plug in negative 1, you get positive 1. Positive 1, again you get positive 1. So it is obvious, it's very clear that this function is not one-to-one. What about this one? You have seen the graph of this function before. This is one of basic functions that we discussed. So this function is one-to-one function. So every time whenever you have different inputs, it always gives us different outputs. But whenever you have a function, how do we determine whether it is a one-to-one or not explicitly? So here I'm giving you an example. Our goal is to do this. We assume that f of x1 is a 1 point from the domain equals to f of x2, some two general points from the domain. We assume that f of x1 equals f of x2, and then if we can show that then x1 equals x2, that means this f function is one-to-one. So let's go for this example. Here I'm giving you the function, and I want to check whether this is a one-to-one or not. Then what I do, I'm plugging x1 to this function, then it becomes 2x1 plus 1 over x1 minus 3, and I equal that into 2x2 plus 1 x2 minus 3. So the same function, one side I'm plugging x1, other side I'm plugging x2, and I'm setting that equal to 0. So if I can show somehow x1 equals x2, that means this function is one-to-one. But let's see how this simplification goes. Here we have two denominators. So if you want to simplify, the best way is to do the horizontal, the cross multiplication here. So when you do the cross multiplication, that becomes this term 2x1 plus 1 times the denominator of the right hand side. That should equals to 2 times x2 plus 1 times x1 minus 3. That is the denominator of the first term, the left hand side. So now we can do the foiling here. We do the 2 times x1 times x2 and 2x1 times negative 3, that becomes negative 6 of x1, and 1 times x2 is x2, and 1 times negative 3 is negative 3. Likewise, you can do the same thing to the right hand side, do the foiling. You can come up with some collection of terms like this. Now if you look at this carefully, you can see here we have 2x1 x2, and also in the right hand side we have 2x1 x2. If you subtract 2x1 x2 each side, you can cancel this one. And the same thing happens here, negative 3, negative 3. If we add 3 to this equation each side, then you can cancel out this negative 3 and this negative 3. So then you come up with negative 6x1 plus x2, but I'm subtracting x1, so that I can cancel out this x1 in the right hand side, and I'm subtracting x2 so that I can cancel this x2 here, so that you can get negative x2 in the right hand side and negative x1 in the left hand side. It's like switching this x2 and this x1. Now you get negative 7x1 in the left hand side, and the right hand side negative 7x2. So if you divide this equation by negative 7, you can prove that is equals x1 and x2. There's a little bit of work, but you can do that step by step. Clearly, slowly you can get this one, and then you can obtain x1 equals x2. So that means your f function has to be one-to-one. So that is a good way of showing whether a function is one-to-one or not. If you have come up with another relation here, then that means this function is not one-to-one. So that's one way of identifying one-to-one functions. Now we can go to inverse functions. If a function is one-to-one, then we call it has an inverse function, or we call it is invertible. So inverse function we denote it by f inverse, like this, f to the power negative 1, and ordered pairs of f inverse are obtained by interchanging the coordinates of each ordered pairs of the function f. So here we're going to talk about the inverse function now. So let's see how we can come up with the relations regarding the corresponding to an inverse function. So here we get take a relation called G to be 3, 1, 5, 2, 7, 4, and 9, 8 like this. First thing that we need to check whether this is a one-to-one relation or not, one-to-one function or not. Here you can see that here the inputs is everything is 3, 5, 7, 9, but we have no the same output any of these pairs. So that means this is one-to-one functions. You can check it. So that means this g function is an invertible function. That means we can make an inverse function. So the inverse function is always obtained by interchanging or switching these ordered pairs, the coordinates of these ordered pairs. So this g inverse function contains 1, 3, which is the value obtained from switching these two coordinates of this pair, 3 and 1, that becomes 1 and 3, and 5, 2 becomes 2 and 5, 7, 4 becomes 4 and 7, 9, 8, 8 and 9, like that. So it's easy to obtain. So now one thing that we can observe here, that the domain of the inverse function is the range of the f function. So for example, the domain of the g inverse function is 1, 2, 4, and 8. But those are the values in the range of the g function, 1, 2, 4, and 8. And the range of the f inverse function is the domain of the f function. Here, the range of the g inverse function is 3, 5, 7, and 9. Those are the values in the domain of the g function, 3, 5, 7, and 9. So you can see that it's switched. So now, how do we find the inverse function? That's the next problem. To find the inverse function for a given function, we use the method called the switch and solve method. It is a step-by-step process. Here, first step, we replace the given function f, replace the f part of the given function by y, and then we interchange x and y, and then we solve that equation for y, and replace this that y by f inverse of x. So by this step we have obtained our f inverse function, and then we can check the domains and the range of f inverse function, because the domain should be the range of the f function and the range should be the domain of the f function. So let's look at an example of a function. So this is our fx equals 4x minus 1. This is just a line. We know that that is a one-to-one function, and the first step is to replace fx by y. So I'm replacing this fx by y, then I can get y equals 4x minus 1. The next step is to interchange x and y. So here I'm interchanging, I'm replacing this y by x and this x by y. The third step is to solve this equation for y. Sometimes it needs some work here. I'm adding 1 each side so that I can cancel this negative 1 in the right hand side. I get x plus 1, and I divide this equation by 4, because then I can get y in the right hand side. Then y equals 4x plus 1 divided by 4. The last step is to replace y by f inverse of x. I'm replacing this y by f inverse of x, so that becomes x plus 1 over 4. So this is our inverse function. And then you can check the domain and the range of f inverse function. Is easy to determine that since this is a line, the domain and the range is negative infinity to positive infinity. Both are the same. Domain and range is same. And for this function also, this is also a line, and the domain and the range is from negative infinity to positive infinity. So that's the end of this inverse functions. But we have one more topic to discuss in this section, and I will upload the next video next week. Until then, Stay safe. Thank you.